Hi everyone, let's talk about questions that were not answered well on the SAC, and this is also a bit of time for me to go through a bit of revision of chapters 1 to 5. So I'd suggest you watch this and maybe now, while it's still fresh in your minds, and also closer to exams, because it goes through really the problem points that you guys, as well as students in the state, find difficult in these chapters. So the first thing we'll be going through is gravimetric analysis, our first analytical technique. Now I think lots of you kind of blow this technique out of proportion, right? It's not that difficult, so we'll just go through it. Gravimetric analysis basically just talks about wanting to find out how much substance there is in a compound or mixture. Now, we've been talking about, let's link this in with what the analytical techniques we've been talking about in class, such as gas chromatography, very sensitive, atomic emission, atomic absorption spectroscopy, and UV visible spectroscopy. These are both very sensitive measures. Now, gravimetric analysis requires us to weigh a sample, right? And it's not sensitive. Okay, so in gravimetric analysis, what we need to do is we need to have our sample, and say we want to find out how much NaCl there is in our sample. We grab a piece of our sample, and what we do is we add it to something that will make NaCl precipitate. Remember that this sample, 3.074 grams, remember always to 3 decimal places, is not just NaCl, because some of you take this mass and then you divide by the molar mass of NaCl, but it's not. It is our sample. It's made up of, let's say that this is sand. What's sand made up of? It actually is made up of calcium carbonate as well, CaCO3. It's made up of salt, of course, of different types of rocks that are insoluble. Remember, that's why we get rid of those in the first place. Okay, and then we add it to something that will allow it to precipitate, so AgNO3. And then we produce our, this is a precipitation reaction, and you need to remember what we are producing. So we've got NaNO3, produces NaNO3. All NO3s are aqueous. All NO3s are aqueous, and we're producing AgCl solid. Okay, how can you remember what's aqueous? Well, I have gone through it with you before, but you guys absolutely need to know this for the exam. No problems. We'll have a put this PowerPoint on Edmodo. But anyway, remember this, okay? This table is very big and frightening for you to remember, but if you remember a few key things, you will always remember it. Okay, snack, always soluble. Remember it, turn it into food. Snack is always soluble. Sodium, so sodium chloride is soluble because of the chloride, partly. But we'll see later on that chloride, some of them are insoluble. Okay? So snack is also always soluble. Sodium's always soluble. Nitrate is always soluble. NO3 is always soluble, even with silver. That should give you a clue. Ammonium, NH4 plus, is always soluble, and potassium is always soluble. Notice that potassium and sodium are in group 1. That has something to do with it, okay? And these all have a 1, either a 1 positive charge, like sodium and potassium, or an ammonium, and a 1 negative charge, like nitrate. Okay? Now, chips are always insoluble, unless with snack, because we already said snack's always soluble. So carbonate, hydroxide, phosphate, sulfur, they will always be insoluble, okay? So unless it's sodium carbonate, which is soluble. Now, Bics are always soluble, bromide, iodide, chloride, sulfate. Notice that chloride, bromide, and iodide are all in group 7. That can help you remember it as well. Sulfate, SO42 negative, okay? They are always soluble unless they're with silver, lead, or mercury. PbSO4, insoluble. You need to absolutely remember this table, okay, because you can get many questions wrong due to that. Okay, I noticed that quite a few of you were confused whether Ag is a positive, whether Cl is a negative, and even when you have your polyatomic ions, okay? This is year 11 stuff, but I'm happy to tell you how I remember it, okay? Because you guys have to remember it. So, if we've got, let's say we've got the periodic table, and for some of you this will be revision, so you can skip past this stuff. But let's say we've got the periodic table, and we have group 1, 2, 3, 4, 5, 6, 7, and 8, but 8 will not form compounds. Okay, so we've got group 1s all the way to 7s. Non-metals and metals. Metals will always be positive. Why? Because they've got group 1 will have 1 electron in its outer shell, group 2 will have 2 electrons in its outer shell. And this is also a metal at the top here, so met, and group 3 will have 3 electrons in its outer shell, right? Group 4 has 4 electrons, 5 and 6 and 7. They've got the same number. The group number tells us the number of valence electrons. So let's say we take one from group 1, sodium, 1 electron in its outer shell. It's not stable like that, it needs 8. It's 2, 8, 1, it's number 11. So it removes this electron, becoming Na+. Okay, so the charge, the valence electrons tell us what charge it's going to have, the valency. Valency is the charge. So Ca2+, it's in group 2. Al3+, in group 3. Now we get over to group 6. Okay, group 5. So let's get over to group 5, and we're going to have phosphorus with a 3 negative charge. Because it has 5 electrons in its outer shell, it wants to gain 3 to make 8. Okay, and then we have something like oxygen, 2 negative. And then we've got something like chlorine, 1 negative. Okay, so that's just a little revision on that. Now let's talk about actual polyatomic ions. Okay, so polyatomic ions, some of you still get a little confused, that's okay, but they can really stuff up your exam scores. So hopefully I can give you a couple of ways to remember these. Okay, so if we've got a nitrate, yeah, this is nitrate. I remember 8 as in I ate a lot of oxygen. So lot of oxygen equals 8. Okay, they only change to 8 and 8 if they are polyatomic, more than one atom, and they've got oxygen. Okay, so if we've got that, we have nitrate, and it's a 1 negative charge. Now the way I remember it is anything with an N, see how these are pointy lines, equals 1. Okay, pointy lines equals 1. So now let's say that we've got NO2 negative. I ate a lot of oxygen. This is, I only had a bite of oxygen. So what do you think it will be? It'll be nitrite. NO2 negative is nitrite. Okay, so now let's say we've got carbonate. Okay, is CO3 2 negative. Okay, now it's 8, it has a lot of oxygen compared to CO2 2 negative, but notice that everything with the C has a 2 negative charge. Okay, it has a lot of oxygen, so this one's carbonate and this one's carbonite. Okay, so we've got those two. Now I remember C, 2 points, 2 charge. C has 2 points and 2 charge. Okay, so now let's say that we've got sulfate. Now the way I remember sulfate is pretty simple too. I just go H2SO4. Everyone knows hydrogen sulfate, which is sulfuric acid, right? And then all we can do is we know that each H has a plus charge, and we have 2 of them, so we have to have SO4 2 negative. Okay, so we have SO4 2 negative sulfate, SO3 2 negative sulfite. So the ites and the eights do not change, right? Depending on they don't change depending on how many oxygens they have. So it's really easy to remember it like that. Now let's do something a little bit left field. Okay, so we have this ClO3 negative, and we've got ClO4 negative, right? Less oxygen. Remember that in sulfate we have SO4 2 negative, SO3 2 negative, but this is sulfate and this is ite. But in nitrate we have NO3 negative, NO2 negative. So it's not like if you've got 3 you will definitely be an 8. Okay, it just depends on each individual atom. So if you're with an N and you have a 3, because we don't have NO4, you'll be 8. If you have an N and you're with an NO2, you'll be an ite. So this one, if we compare the two, we can see this one has less oxygen, so it will be chlorite, and this one will be chlorate. And Cl has this big 1 here, equals a 1 charge. Okay, so these are just the anions. Remember that everything that's polyatomic, besides ammonium, but we should all know that, and a few other exceptions, will be an anion. So make sure you've got that negative charge there. So let's get back to the question. This question was answered particularly badly in the SAC, right? So we've got, I gave you the procedure. I saw lots of you reading the procedure. You don't need to read it because you've already done it. It's just there if you've forgotten what you added to what. Okay? Now, I would just go straight to the question. One particular student, when doing this experiment, added too much barium chloride to the filtrate. What effect would this have? Okay, barium chloride. What are we trying to look at? Quickly look back. To find the percentage by mass of sulfate in a brand of a fertilizer using barium chloride. Okay, so if we've got sulfates, SO4 2 negative, remember, plus Ba2 plus produces BaSO4. Now we want to look at this, okay, i.e. this doesn't matter how much we add because they will just be, even if we have left over, they will just be cations floating around. They won't be with our precipitate. We'll wash it. Okay, so have a look. Barium chloride, drop by drop, blah, 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 blah. If more precipitate forms, add more barium chloride. Look, 3 mils. We're just adding as much as we can until all of the sulfate has reacted. We want to add in gravimetric analysis, we have NaCl, what we want, plus NaNO3, AgNO3 in excess. This is because in our conical flask, when we have our Cl negative, Cl negative, Cl negative, right? Remember, Na is just a spectator, okay? We will have Ag, Ag, Ag. Even if we add more, who cares? And we will end up, once they have reacted, once we've given them time to react, we will end up with AgCl, 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 3 of those, and then extra Ag, I think just 2 more. Yeah, so Ag. Now when we are filtering, we're just going to have our precipitate, which is just AgCl, AgCl, AgCl. And remember, we wash our precipitate. What does that do? Well, it rinses out all of the soluble ions. Rinsing, washes out all soluble ions. Why do we do this? Because the soluble ions will increase the percentage by mass of our precipitate. Okay, it'll give us the idea that our precipitate is heavier than what it is. So what effect will it be to add excess? None, because you want to add it in excess. Because need to make sure all SO4 negative is as reacted. You can even add in excess will be washed off. Precipitate. Okay, so that's just a little summary of gravimetric analysis. Okay, now empirical formulas. So I know that you're all familiar with actual empirical formulas, and if you've got a percentage of C, a percentage of H, and a percentage of O, you can work out the mole ratio. But I want you to treat these in the exact same way. Now you can skip past at any time if you got this question right. But let's have a look. We've got CuCO3, one component of our formula, and we've got H2O. Now, this can be actually treated as CXHY, where we don't know the numbers there. It can be treated as a regular empirical formula type of question. We know our mass, we know our mass of CuCO3 equals, tells us, just our CuCO3 equals 1.565 grams. Do we know our mass of H2O? Well, we know the mass of the initial, which is CuCO3 x H2O, and we know our mass of the CuCO3 by itself, so it must equal the mass of H2O. Okay, and I think a lot of you got to this point, so it equals the mass of the initial equals 3.000 grams minus 1.565 grams. Okay, so if we just quickly do that, the mass of water equals 1.435 grams. Okay, so we know the mass of C or whatever. It's 1.565 grams. It's this here. We know the mass of water. Okay, so let's just set it out like an empirical formula. So, how we work out an empirical formula. So it is the mass over the molar mass. isn't it? So if we got our mass, 1.565 over the molar mass of CuCO3, and then we've got a ratio with 1.435 grams over the mass of H2O, the molar mass of H2O. So let's just keep going on this side. So 1.565, right? So let's work it out. 1.565 divided by, and 1.435 divided by 18 equals 0.0797, and here we've got, let me quickly work it out. One, two, 3.5. 1.565 divided by answer. Okay, now we divide this by the smallest value, will give us a 1, 2.07 6.289 is about a 1, 2, 6. 6 waters of crystallization, so our formula is okay, 6 waters of crystallization. Okay? All right. Parallax is not one for gravimetric. Okay? Our burette is adding excess of the thing that we want to precipitate with, so it wouldn't really matter if we were at a mil under or whatever, because we keep looking at it and checking and making sure. But gravimetric, there are a few things that could go wrong. Okay? So what are these few things? Well, we've got, so let's say not enough barium chloride, BaCl2 added. That's possible. That's considered an error because it's really hard to tell if all of it has been added. That's why some of you are saying, oh, but isn't the endpoint isn't overshooting a mistake? Well, it can be considered an error because of the human eye, right? So not enough BaCl2 has been added. Okay, now another one. A student received low. So what would this make it? Not enough BaCl2 would be added. So decrease the mass of the precipitate, decrease percentage. Not enough BaCl2. Okay, so now wasn't washed. Washed completely. Okay, wasn't washed completely. This would increase the mass of the precipitate and decrease the percentage. Okay, so this is also, and increase the percentage. Okay, so this is also another error just because that's the fault with gravimetric. It's relying a lot on our experimental skills. Okay, so another one is might not have some of the precipitate through the filter paper. If filter paper too coarse. Okay, that would decrease your mass of your precipitate and decrease your percentage. okay, because some of it would be gone, less to weigh. Okay, something else, not completely dry. Not completely dry, okay, that would increase the mass of your precipitate and increase your percentage. Okay, so that's pretty much gravimetric. So let's move on to volumetric. Okay, so volumetric. You guys are pretty good at volumetric, actually. Okay, so volumetric analysis. Obviously overshooting. Okay, now overshooting, if you're doing a regular volumetric analysis, let's say we've got our known in our burette, and in our conical flask we have our unknown, right? So if we've got our known in our conical, in our burette, and we overshoot with our known concentration, it'll say that there is more here, so higher concentration, okay, higher percentage by mass. Okay, and you know your rinsing ones. I'm not going to go through them. Now, what else could we do? Now, let's say that we're doing a back titration. This is where you guys stuffed it up. Back titration. Okay, let's say if we overshoot. Okay, this is the one where most of you actually got this wrong. Okay, so we're overshooting, but we're overshooting and we're getting concordant results. Okay, we're overshooting, but we're getting concordant results. Okay, if you want to bring in systematic and random, this is systematic. Same sign, i.e. it's always being either positive or negative, and the same size. Okay, the same size error, leading us to get concordant results. Okay, so if we overshoot, so remember, back titration. Let's quickly draw it out. I've drawn this out 100 times, but let's draw it out again. Initially, we have our excess, let's just say HCl, and we've got CaCO3 here, and then we're titrating with NaOH and our excess HCl, right? Okay, so let's say we're doing that, and we've got excess HCl, and here we're overshooting. If we overshoot, it is like we have more HCl in our conical flask. If we have more in our conical flask, less HCl reacted, meaning that there was less CaCO3 than there actually was, leading us to a lower percentage by mass of CaCO3. Okay, so overshooting in back titration, opposite to regular titration. Okay, what we did is we got our chalk and we reacted it with 100 mils of HCl. With 100 mils of HCl. So this is obviously our first step, excess HCl. Okay, we've got our excess HCl and we've got our calcium carbonate, right? Now the mixture was then filtered into a volumetric flask made up to 250 mils. A 25 ml portion of this was then reacted with sodium hydroxide for neutralization. So We then have our sodium hydroxide and then our HCl excess. Okay, so let's work this one out. Okay, so let's say that we've got no max. Okay, let's say that we have to do question A. Write out the two full reactions. So the first one we know is HCl aqueous plus CaCO3. And now some of you are confused here. At first the chalk is a solid, but then we weigh the chalk and we react it with 100 mils of HCl, right? So it's actually in solution when it's reacting with the HCl. However, they would take solid as well. Okay, they would actually take it as well because technically chalk was in a solid state. Okay, now what do we produce? A salt plus a water plus a carbon dioxide. So the salt would be CaCl2, right? And we have aqueous. Remember, all Cls are aqueous unless they are... All Cls are aqueous unless they are with silver, lead, or mercury. So we're in the clear with calcium, okay? Plus a H2O liquid plus CO2 gas. Okay, obviously carbon dioxide will always be a gas. So let's quickly balance this. We've got Ca, okay, we'd need 2 of these, okay. Bang, that's already your mole ratio. So let's see CO3, everything else seems to be fairly balanced, right? Okay, so now let's write out the second equation. Some of you got confused and started writing this, a salt, plus our base is going to make something. That's just not going to happen, okay? We have to remember the back titration where we add something in excess and then we react whatever's left over with our strong base. Strong acid, weak base. Strong acid, strong base is our final titration, regular titration. So we have HCl aqueous plus NaOH aqueous, and this produces H2O liquid plus NaCl, all 1 to 1. Very nice. Okay, so that would get you the 2 marks. Okay, so now let's determine the percentage by mass of calcium carbonate in impure chalk. So notice I've taken away your baby steps. Okay, so we just have to use our own knowledge of baby steps. Okay, what are we given? 25 ml portion of this is required to react with 8.5 mils of 1m sodium hydroxide. So we can work out the moles of sodium hydroxide. This is great. This is here. We can work out the moles here. Okay? The moles equals CV equals don't forget to put it into litres, 0.0085 times 1 equals 0.0085 mole. Okay? So, next step, we've got the moles, okay, of NaOH in the 25 mil. In 25 mil. So we have the moles of HCl, right, in excess in 25 millilitres, right? We have the mole of HCl in excess in 25 millilitres. But remember, the initial solution was actually 250 millilitres. Okay, let me give you a reminder of dilution. Okay, let's say we have a conical flask and we've got 1 mole of HCl, right? And then we add water, right? So we start off like here. Got 1 mole there. We add water. Up to here. We still have 1 mole of HCl. Okay? We still have 1 mole of HCl. If I'm adding water, all I'm doing is changing the concentration, changing the conc, okay? So how will I change the moles? Well, if instead of adding water, I actually take out a piece of the pie, right? I take an aliquot, okay? Technically speaking, it would be an aliquot from our pipette, right? Our pipette would bring us our aliquot, and we might have, that's less than half, it's like a quarter, so 0.25 mole of HCl. But here, the concentration stays the same. So if you're taking an aliquot, changing the mole, keeping the concentration the same. If you are adding water, you are keeping the mole, but the concentration changes. We're diluting it. So in excess, in the 25 ml, but I actually took it from the 250 ml, so the mole of HCl in excess in the 250 ml, right? How can we work it out? Well, we can write a little equation, which is what I've been showing some of you. So we can go 0.0085 in 25 mils, right? There will be X mole in 250 mil. And we can just simply turn this into a ratio. Okay, so we just times it by 10, really. So the mole HCl excess in 250 milliliters equals 0.085 mole. Okay, so we have this mole now. Now we actually have this mole that, oh sorry, not that mole, but the mole that was left over. Okay, so the mole that was left over, all we have to do to find out how much reacted, how much HCl reacted, equals initial minus excess. So how can we work out the moles of the initial? The moles of the initial, we've got it here, 100 mils of 1 molar. So equals 0.1 times 1 equals 0.1 moles. Okay, the moles reacted equals 0.1 minus 0.085 equals 0.015 mole. Okay, now if we have this moles, we can work out easily that mole. So the mole of the CaCO3 equals 2 over 1 times, right? No, sorry, not 2 over 1, 1 over 2 times 0. Equals 0.0075 mole. That's how much mole there were in our 0.8 grams of chalk. So let's work out the mass of calcium carbonate. Remember, the 0.8 grams is not the mass of chalk, is not the mass of calcium carbonate. It's the mass of chalk. It'll be made up of salts and all different things. So the mass of calcium carbonate equals N times M equals 0.0075 times, right, times by, can't be bothered working it out, but I haven't even worked it out there. Okay, well, calcium is 40.1 plus 12 plus 48, right, equals 100.1 times 0.0075. 0.75075 grams. And to get the percentage, we do mass over total equals 0.75075 over 0.8 times 100, of course. equals 94% to one significant figure. Okay, to one significant figure, it would be 9 times 10 to the power of 1%. Okay? Alright, so now skip ahead to question 8. Is it this one? Yep. Okay, so you guys actually did the volumetric question brilliantly. I think the average was about 91% for that, and that was working out the molarity of a standard solution. Okay, and I think what stuffed you guys up here was we have a symbol of hydrated ethanedioic acid crystals, right, of mass this. This mass includes water, and it was dissolved in 250 mils of water. So this question, calculate the amount of mole in the 250 ml standard solution. All we needed to do, the moles of this equals mass over molar mass equals 0.2145, right, divided by, and the molar mass includes the water. That's where lots of you lost the point. Okay, so we've got 12 so that's 90, this is 90, and this is 2H2O. So it's 2 times 18, right? Would give us a molar mass of 126 equals 0.2145 divided by answer. This mole, right? Okay, so significant figures, oops, we can even go further, we can go to 4 sig figs, right? Because in assuming sig figs, we assume that the values in data book, are actually infinite. We don't take them into account when determining significant figures. Naming the oxidant and reductant. Well, you just need to go through and see which has changed oxidation numbers. So let's go through it now. Okay, so we've got our oxygen, which is a 2 negative, right? So negative 14 altogether equals negative 2. This is the final value we need to get to. And we've got x minus 14 equals negative 2. And so it would be 12. So plus 6. Now let's have a look at chromium on this side. We have a plus 3. Plus 3, right? So chromium has been reduced. So it is the oxidant. You can write Cr2O7 2 negative, or you can write Cr2O7 2 negative. The only reason why you can write this one is because there's only one species with chromium, right? Remember when we had the nitrogen, we had to be very specific. So the reductant, let's have a look. It is ethanol, right? Converting to ethanoic acid, but let's work out why, okay? This was a little bit more difficult than what you might have expected. So now we'll draw it out to make it a little bit easier to see. So we've got our CCO H, 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 H. Okay. Now, and we'll draw out our other one. C, H, H, C, double O. Now, what needs to stay the same, or what most likely will stay the same? This plus 1, plus 1, plus 1, plus 1, plus 1, plus 1, and this one 2 negative. Okay, so in order for these to balance, we have to take this part separately to this part. In order for these to balance, we have a 3 plus charge, and so we will have a negative 3 charge here. In order for these to balance, we have a plus 1, plus 1, plus 1, minus 2. Okay, so 3 minus 2 is 1, so we have a negative 1 here. Okay, now let's work out this one. Plus 1, plus 1, plus 1, plus 1, negative 2, right? And negative 2, negative 3, and we will have a minus 2 is minus 4, plus 1 is minus 3, so carbon is plus 3. So everything stays the same except for this carbon goes from a negative 1 to a positive 3. But the way I do it is I know that oxidation, right? 2 ways you could do it, you know, with what you know now and not have to go into so much detail. Write the half oxidation reaction. Try it out, okay? Or, you know, oxidation is the gain of, the loss of electrons or the gain of oxygen, and we've actually gained 1 oxygen. That's a really easy way of doing it. So our reductant is ethanol, or in other words, the second C, right? The second C in ethanol. If you wanted to be very specific, they would be very shocked that you would know that. But anyway, that was a tricky one. But I would go right out the half oxidation. You know that you'll have electrons on the right side, so it has lost electrons.